Here is one more example using our surface area formula. Let S be the surface formed by rotating the curve. X is equal to cosine z. Y is equal to 0 for z between negative pi over 2 to pi over 2 about the z-axis. Find its surface area. So before we do anything else, we should be drawing a picture here. Z runs from negative, that should be positive pi over 2. Down here is negative pi over 2. And then x is cosine of z. And so we have this curve here. Here's our x-axis, here's our y-axis. So this is the curve x is equal to cosine z. And what we're going to do is that we're going to take this curve and we're going to rotate it around the z-axis. So it's going to look like this. The textbook has a better illustration of it perhaps, and this looks like a football-shaped region. Okay, how are we going to parameterize this? Well, there's going to end up being two parameters involved. So the first parameter is going to correspond to the z-coordinate. The first parameter is going to correspond to the z-coordinate here. It's going to tell you how far up and down you are along the football. And then the second coordinate is going to tell you how much you get rotated around by. So we start here, we rotate around. And so I'm going to take u to equal z, and that will be our first coordinate. And then theta is the angle of rotation. So we're going to write our parameterization in terms of u and theta. Okay, how do we go about doing this? Okay, so we have r of u comma theta. So we know we're going to have three slots here. The first thing is that we're just identifying u to be z. So z is equal to u. As for the x coordinate, so we start off with x is equal to cosine z, when z gets replaced by cosine u. But that's not our final answer. That's the point that we could rotate from. So in the xy plane, this point right here is going to be x is equal to cosine u. But then we're probably going to rotate it by some angle theta. And rotating by this angle theta is going to correspond to multiplying cosine u by cosine of theta. So this is going to give us x is cosine u times cosine theta. Another way to think about it is that cosine u is playing the role here of r in polar coordinates in some sense. It's going to be the distance you are away from the origin on the circle here, and then we multiply by cosine theta and sine theta to get x and y. So that shows us then that y should be cosine u times sine theta. So here's our parametrization. What are the bounds here? U is z. We know z runs from negative pi over 2 to pi over 2. And so then we have that. Theta, it's a trip around the circle. Theta runs from 0 to 2 pi. Okay, so at this point then, we know we need to be using this formula here. So we need two partial derivatives. R sub u is going to be negative sine u times cosine theta, negative sine u sine theta, and 1. R sub theta partial derivative will be negative cosine u sine theta and cosine u cosine theta and 0. So when we take the cross product here, I hat, j hat, k hat, negative sine u cosine theta, negative sine u sine theta, and 1, negative cosine u sine theta, cosine u cosine theta, and 0. Okay, so taking the cross product here, the I hat component is this times 0 minus this times this. So negative cosine u cosine theta. The j hat component is this times this. It's negative cosine u sine theta minus this times this, that's 0. And then the k hat component is this times this. That would be negative sine u cosine u times cosine squared theta minus this times this. So that would be minus sine u cosine u times sine squared theta. The cosine squared theta and sine squared theta, that will become 1 here. 1 times negative sine u times cosine u. And our magnitude of the cross product is going to be the square root of negative cosine u cosine theta squared plus negative cosine u sine theta squared plus negative sine u cosine u squared. And so this is cosine squared u cosine squared theta plus cosine squared u sine squared theta plus sine squared u cosine squared u. Okay, cosine squared u times cosine squared theta plus sine squared theta. That just becomes cosine squared u plus sine squared u cosine squared u. We can factor out a factor of cosine squared u here, and we end up with cosine squared u times 1 plus sine squared u. And this is equal to cosine u times the square root of 1 plus sine squared u. Now, usually we have to be careful about moving a square outside of the square root. In this case, because our bounds here are z is u between negative pi over 2 and pi over 2, cosine of u is always positive, or at least non-negative on this interval. So this checks out. So then our surface area integral is going to be the integral. U runs from negative pi over 2 to pi over 2. Theta runs from 0 to 2 pi of the magnitude of our cross product here, cosine u times square root of 1 plus sine squared u du. D theta du. Okay, how to finish off this problem here? Let's do it with substitution. So this square root here is kind of nasty, but if we replace u, we replace sine u with u. Oh, can't do that. That's repeating letters here. So let's use w is equal to sine u. If w is equal to sine u, dw is equal to cosine u du. So oops. There is our dw here. And so this is going to be theta runs from 0 to 2 pi, and w runs from -1 to +1. W runs from -1 to +1, because sine of -pi/2 is -1 here, yep. And square root of 1 plus w squared dw d theta. At this point, I am just going to skip to the final answer here. There's a trig substitution you'd have to do to integrate this. So you end up with 2 pi times square root 2 plus the natural log of 1 plus square root 2.